Hey everybody, this is Chili. Welcome back to Intermediate C++ Tutorial 1. And today we're looking at memory, binary numbers, variables. And I know you're saying, Chili, don't fucking patronize me. I know what a variable is, for Christ's sakes. And I'm saying, nah, you don't know it like I'm going to explain it to you today. We're going real deep. We're going in balls deep. I can't even go 1 minute without making it inappropriate. But anyways, so... I'm going to give you a lot of background and theory because A, it's going to help a lot of you in understanding how pointers and memory management works. And B, I just think it's pretty funking interesting shite. And, if you feel like I feel, baby, then come on, woo, let's get it on. So the first thing I want to talk about is memory, and when we talk about memory, we generally mean RAM. So what is RAM? Well, it stands for Random Access Memory, and that means you can access any part of the memory in any order you like. You can have it your way, as opposed to, this bullshit. What I mean by access any part in any order is it works basically like a one-dimensional array. So like, say you got some array, right? It's made up of a bunch of elements that are just lined up in a row, and when we want to get at one of the elements, we call it by its index. So every element has an index. That's the number that we use to identify the element in the array. And in memory, it's the same idea, only we don't call them elements. We call them locations in memory, and we don't call them indices. We call them addresses. But essentially, it's the same old bullshit. And every element of our memory, every location, is a byte. B-Y-T-E. We'll talk about that a little bit later. Alright, now let's take a look at a little bit of an in-depth example of how the CPU goes about its business. So we got here a very simple line of C++ code. C is equal to B plus A. So how does this work? Well, first thing that's going to be done is, C, B, and A, they're variables, they're stored in memory. So what the CPU has to do is it has to load those values basically into itself in order for it to work on them. Now the CPU has some special storage locations that are basically built into its core circuitry, and they're called registers. You can think of them like the hands of the CPU, and they're what it uses to do its work. So, first thing we're going to do is we're going to load the variable B into one of our registers. The CPU doesn't think of these things. From the CPU's point of view, A, B, and C, they don't exist. It only thinks in terms of numbers. So, from its point of view, it's going to be loading from address 27577 into, this register here. And similarly, it's going to load from 27576 into this register here. The second thing it's going to do is going to add them together, and what it does is it just adds one of them to the other. So let's say it adds this one to here. The result, now this register is going to store the value 69. And the final thing that's got to do is it's got to store that result back into memory, into the variable C. So it stores this value into 27578. And there you go, that is this line of code accomplished. So to summarize, RAM is basically just an array of bytes. Each address in the RAM corresponds to a single byte. A byte is made up of 8 bits. Great. So the question is, what the fuck is a bit? Well, to understand bits and bytes, you really have to know a little bit about the binary number system. So I'm going to give you a little crash course in binary. Now, circuits work with two main states, on and off. A bit is a symbol or a value that can represent two states. So basically, we can use bits to represent the states of lines in a circuit or the states of memory cells in some kind of storage. Now, a single bit has, again, two possible states. And when we use bits to represent the states of an electrical circuit, for example, we usually say that 0 represents off and 1 represents on. So here, a single bit, two possible states, just like a line in a circuit. Now, if we put 2 bits together, how many possible states do we have? Well, we got 0, 0. You can have the combination of 0, 1. You can have the combination of 1, 0, and you can have 1, 1. And so we got 4 states if you combine 2 bits together. And we can label those, we can give them, numbers. We can say this is 0, 1, 2, and 3. 3 bits, how many do you think that gives you? Well, if you write out all the combinations, you'll see that gives you 8 distinct states. 0, we can label them 0 through 7. And now you can kind of see a pattern here. It doubles every time you add a bit, which makes sense because every bit has 2 possible states. So, for example, number of states you can have with a single bit is 2. Number of states you can have with 2 bits is 2 times 2 equals 4. 3 bits is 2 times 2 times 2 equals 8. And you can write this out as 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so forth. Now, like I mentioned, a byte is a value that has 8 bits. So you do the math, 2 to the power of 8 gives you 256 different possible states. And if you label them 0 to 255, you have what in C and C++ is called an unsigned car. So an unsigned car is just a variable whose value can range from 0 to 255. And the number 255 might be familiar to you, especially if you played some old school RPG games. It's a common number for the max that you can have for a stat. And that's a big clue to say, oh, the programmers of this game, they're using an unsigned car to store this stat. And I'm going to talk more about the different integral types that we have in the next section. Right now, I want to talk quickly about a misconception that people have. And that is, for example, people look at binary and decimal and they'll treat them as completely different things. Like they'll think, okay, some numbers are stored in binary and other numbers are stored in decimal. Wrong. Or they'll say something like, pointers are different than integers because pointers are stored in hexadecimal and integers are stored in binary or decimal. Wrong. Totally wrong. All right. Values, numbers are just numbers. Writing a number in binary and then writing it in decimal doesn't change the meaning of the number. It's still the same value. Okay. If I write the word pubes in 2 different fonts, does it change the meaning of the word? No. Pubes are still gross no matter what font you write them in. Now, the storage of the computer is an electronic circuit, and so it's binary based, and that's why you have ranges like 0 to 255 because that fits in the binary storage of the computer. But the number is still a number. It's still the same number regardless of how you write it out. Humans have 10 fingers, and that's why it's thought that many, not all, but many civilizations went for a decimal counting system. And computers have, 2 fingers, 2 electronic fingers, and that's why it makes sense for them to organize their counting in binary, and that's all there is to it. By the way, a little trivia, the name bit stands for binary digit. And byte is basically, it's based off of that. A byte is a little bigger than a bit. But, obviously, if you were to spell it B-I-T-E, that would be kind of, confusing. So they switched it up. They put a Y in there instead. And a little more trivia, a 4-bit value is called a nibble. Oh, isn't that cute? And the reason why we give 4-bit values a special name is because they come up a lot in hexadecimal. All right, just a quick thing now about hexadecimal because it comes up a lot. Hexadecimal is another counting system. Just like decimal has 10 symbols and binary has 2 symbols, hexadecimal has 16 symbols. And the reason why this is useful is because it basically lines up very nice with binary. So as you can see, the hexadecimal 0 through F fits neatly into 4 binary digits. It goes from the lowest value of those 4 binary digits to the highest value of those 4 binary digits. So hexadecimal lines up very nicely with binary. You can write some hexadecimal like AF62, and you can figure out the binary very quickly just by going, well, what is A? It's 1010, F is 1111, 6 is 0110, and 2 is 0010. You can convert them very simple. If you asked me to convert, this number into decimal, that would be a different story. It's complicated. And the reason why it's complicated is because we'll look at hexadecimal has 16 symbols. 16 is equal to 2 to the power of 4. And that's why it takes 4 bits to make one hexadecimal digit. So hexadecimal lines up very nicely with binary. And the reason why we use it is because, obviously like a big binary number, like let's say, 64 bits, that's a fuck of a lot to shit to write out. So it's easier to read and write hexadecimal sometimes. So that's why you see it in a lot of places. Like, for example, pointers. It's mostly just a human convenience thing. It's a representation. Don't ever let me catch you saying pointers are stored in hexadecimal, because I will punch you in the face. Now, what were we talking about again? Oh yeah, so that's what a bit is, and that's what bytes are. And you might be asking, well, chilly, but if memory is just an array of bytes, how can we have something like an int? An int typically has a range of, somewhere like -2 billion to +2 billion. That's 4 billion different states. But our memory locations, they can only store bytes, and bytes can only represent 256 different states. So how do we store our ints if all we've got is bytes? Well, think about it. A single bit can only have 2 different states, 1 or 0. But you put 2 bits together, and now you can have 4 states. So what if you put 2 bytes together? Well, 2 bits together, that's just 2 states times 2 states equals 4 states. So 2 bytes would be 256 times 256 equals, about 65,000 states. And if you put 4 bytes together, that's 256 to the power of 4 equals about 4 billion. So, and that generally is how an int is stored in memory. So if you've got some variable, call it int pubes, and it lives at address 4, that means that it actually occupies addresses 4, 5, 6, and 7, 4 bytes. And now you remember I told you that the CPU is able to access memory 1 byte at a time. That's the smallest granularity that it can access it at. It can't grab single bits, or it can't grab a nibble. It can grab, the smallest it can grab is a byte, but that's not the largest it can grab. So it can grab these 32 bits, these 4 bytes, all in one go and load them all at once. 32-bit CPU, or a CPU running in 32-bit mode, can do that. If it's running in 64-bit mode, then it can grab at most 8 bytes at once. There are exceptions, but in general, that is the limit. And that's how data types larger than 1 byte function. They're basically loaded and stored as a single unit. This would be loaded into a register, and it would have the value then 000000FF, which means 255. All right, let's talk about the types of variables now. What are the basic primitive types that are built into the compiler, and what are their ranges? Well, you've already been using a few of them for a while now. We've got int, good old int, and its range is -2 billion to +2 billion. We've got bool, it's a Boolean value, true or false, and we have got float, which has a range of 3.4 exponent 38 plus or minus. And what the hell does that even mean? Well, That just means 3.4 times 10 to the 38 to negative 3.4 times 10 to the 38. So that's a 3 followed by a 4 followed by 37 zeros, which is, pretty damn big number. And I'll talk a little bit more about how floating numbers are represented internally a little bit later in this video, just as a bit of like trivia. It's not important, but just for those who are interested. So those are the primitive types that we've been using so far, but there are other types of basic variables in the C++ standard. So we've got other integer types besides int, and I've already kind of talked about one of them, which is unsigned char. Char is just negative 128 to 127. This is the smallest integral type that you'll be using, and it's generally used a lot for text, for storing text information. So every char will store one character, and that's why they call it char. But it's just an integer number. There's also short, which goes from about negative 32,000 to positive 32,000. Finally, there is long, which goes from this to the, it's a really big number. I don't know, a million, billion, trillion, quadrillion. So negative 9 quintillion to positive 9 quintillion. It holds very large integers. And for floating point numbers, there's also a larger floating point type called a double. And that one has a range of, negative to positive 1.7 exponent 308. So, about 307 zeros after this number. Again, very large numbers. Now, for every signed integer, which is to say every integer that can have a negative value, there is also an unsigned version of that integer. So we have int and we have unsigned int. And the difference is that unsigned ints can only have positive values. But because they only have positive values, the upper range is going to be higher, right? Because it doesn't have to waste states on encoding the negative values. So, for example, int goes from negative 2 billion to positive 2 billion. Unsigned int goes from 0 to positive 4 billion. And similarly, you have, unsigned char, which goes from 0 to 255, unsigned short, which goes from 0 to 65,000, and unsigned long, which goes to, 18 quintillion. Now, floating point numbers are encoded such that they're always signed, so you never have an unsigned float. It doesn't exist. And as for bool, the concept of positive and negative doesn't really apply here, so unsigned bool makes no goddamn sense. Now let's consider the amount of memory each of these types takes up. It's probably easy to see that a type with a larger range is going to take up more space in memory than a type with a smaller range, right? Like if we look at an unsigned char here, the space that it takes up is 1 byte in memory, and the range that it has is 0 to 255. So that is 256 states, right? And so 1 byte is equal to 8 bits. 2 to the power of 8 is equal to 256. So with 8 bits, you can represent 256 states. So that represents 0 to 255. Or you could also represent that as negative 128 to 127. That would be char. And this would be unsigned char. All right. Now, for an integer, what's the story there? Well, an integer goes from negative 2 billion to positive 2 billion, or an unsigned integer, even better, goes from 0 to about 4 billion, and it takes 4 bytes. Well, let's do the math quick. So 4 bytes is equal to 32 bits, 2 to the power of 32. What do you think that's equal to? It's about equal to 4 billion, right? And that will give us either, negative 2 billion to positive 2 billion, plus or minus 2 billion, or it'll give us 0 to 4 billion. Now, a couple things to notice. Notice that all of these variable types, their size is all a multiple of 1 byte. You don't ever have a variable that's like 12 bits or 15 bits. They're always going to be multiple of 8 bits or a multiple of 1 byte because the CPU can only access at the byte level. It can't access half a byte or something. Another thing you might notice is that, taking a look at these integer types, the smallest type is 1 byte. The next largest type is going to be 2 bytes. Then the next largest is 4 bytes. And then the largest after that is 8 bytes. So you see the size doubles every time. And that has to do with the way the CPU accesses memory. It can't access 6 bytes at a time or 3 bytes at a time. It accesses in multiples, or not multiples, powers of 2. And you can see that here. I mean, 2 to the power of 0 is 1, that's a car. 2 to the power of 1 is 2, that's a short. 2 to the power of 2 is 4, that's an int. And 2 to the power of 3, 8, that's a long. Now, some of you might be asking, well, why is it that the signed variable types, they have the same size as unsigned? They're both 4 bytes long, but the signed ones can only store 2 billion, unsigned can store 4 billion. And the answer to that is, well, in the unsigned, we don't have to worry about encoding negative numbers, so we can use that space to add extra positive range. But with signed numbers, you have to be able to encode the negative and the positive, so that's why it can only go half as high. But they both still encode the same number of states. And you might also be wondering, well, how do you encode the negative numbers as binary? How does that work? And basically, it uses something called 2's complement. It's kind of complicated. Luckily, we don't have to worry about that detail, so I'm not going to cover 2's complement here. But if you're super interested, you can look it up yourself. Now, for the floating point numbers, a float, or a single precision floating point number, it takes up 4 bytes in memory. And a double precision floating number takes up 8 bytes, so it uses twice as much space to get that bigger range. And just as a little bit of trivia, let's look at the representation of how a single precision floating point number is represented in memory. So the way it works, it's quite a bit different than an integer. It's broken up into 3 parts. You got the fractional part, the exponent part, and then the sign bit. So the fractional part gives us something, it'll give you something like this, like 2.1416 7 or something like that. You get a number like this. The exponent part now gives you the magnitude. So it's an 8-bit number, and it's going to give you, times 10 to some number here. So let's just say, 12, which will make this a very big number now. And then the 1 bit for the sign tells us whether it's negative or positive. So you take these 3 parts, these separate parts, you put them together, and you get a floating point number. I mean, obviously, it's not going to be the way it's actually encoded in memory. It's not like times 10 to the something. It's more like 101101 times 2 to the power of something, because it's binary. But you get the idea. It's the same idea there. And for a double, it's the same idea, only you get, you have more bits. With a float, you've got 32 bits. With a double, you've got 64 bits to work for. So you get way more bits in the fractional part, which is also called the significand. And you get a few more bits in the exponent part. And again, the sign is still only 1 bit. So double has a lot more precision and also a little bit more range. But generally, we don't have to think about this bullshit when we're working with floating point numbers. We just treat them as, normal, real numbers. If you're thinking about this shit all the time and worrying about it when you're programming, you're probably fucking doing it wrong. Now, the last one I'm going to talk about here is the bool, and it's a little weird. The bool takes up one byte in memory, but it only has 2 states, true or false. So technically, you would only need a single bit to represent the range of the bool type. But we use a whole byte, so it's kind of wasting 8 times as much space as you need. And you might think that's really inefficient, but the thing is, is that the CPU, like I've mentioned before, the CPU can only access 1 byte at a time. It can't address single bits. So that is why we store the bool as a single byte in memory. You can do some, bullshit tricks to pack in multiple, basically packing in multiple bools into a single byte, but usually it's not worth the hassle. So we generally just stick to the 1 byte bool for the most part. Now, there's one last little detail that I gotta mention here, because if I don't mention it, people are gonna yell at me in the comments. And the detail is, I told you that an int is 32 bits, but here's the thing. That size and that range, that isn't actually set in stone. So what the standard tells us is an int must be at least 16 bits. So it can be no smaller than 16 bits in size. Now, generally, in almost all the compilers that you see compiling for, general desktop computers, it's going to be 32 bits. But the standard says it could also be 16 bits. And back in the day of DOS and 16-bit computers, it was 16 bits. So technically, int is not fixed to 32 bits. And it's actually the same story for short. Short is not fixed, and it is also stated to be at least 16 bits. But in reality, in actual practice, an int is going to be 32 bits, a short is going to be 16 bits, a char is going to be 8 bits, a long is going to be 64 bits. That's how it is for most common architectures. And just keep in mind that this is not hard 100% guarantee, it's just like 99.9%. Now, for the times when it really matters, when you really have to be precise about the sizes and ranges of your data types, there are special integer types that came in C++ 11, and you can specify, I want an integer that is 8 bytes, or that's 16 bytes, 64 bytes, etc. But for most use cases, it's not a big deal, and you can just go with the standard int, and that's what we're going to be doing for the most part, I think. And that's pretty much all the basic data types, except for pointers and references, which are a kind of pointer, really, because we haven't covered those yet. But besides that, it is from these basic building blocks that all the data types that you see are built. So classes, like for example, std random device or something, if you break them down enough, all you end up with are these basic data types. And of course, arrays are just arrays of whatever data types, which can be broken again down into these fundamental types. Everything is made out of this shit. Alright, now to finish off this video, I want to take a quick look at how the compiler organizes variables in memory and how it translates your C++ code into CPU operations. Now, what I'm going to be giving you here is a simplification of the story. It's not the full story. I was originally going to give you all the gory details, but that video ended up being too long and too hard. Like a madik. And so scrap that. It still exists, and I'm going to link to that video at the end of this one, but it's not required to follow through this series. It's not going to be part of the canon, alright? Alright, to start off here, let's take a detailed look at the example I gave before, the z is equal to x plus y. So the first thing that the compiler does is it takes a look at this code here. It says, okay, you got 3 local variables. So we're going to give them spaces in memory, x, y, and z at 1000, 1004, 1008. And now it's time to translate this code into CPU operations. So first thing we're going to do is we're going to initialize x. So we're just going to put the immediate value of 5 into the integer at address 1000. That looks like this, right? 05 at the lowest address, and then 000000. Right? This number looks like this if you write it out. 0005. If you write it out like this, it looks like this. But this convention, by the way, of storing the lowest order byte in the lowest address is called little endian. And there's also big endian, which would have this byte down here. But yeah, x86 processors use little endian. Now we'll do the same thing for y, but we'll be storing the value 3. And then here's where it gets interesting. We've got to calculate x plus y and store the result in z. So the first thing we've got to do is we've got to load those values into registers in the CPU so it can perform the operation. So if we want to load x, all we got to do is we got to go the int at 1000 and store that into A. And that's going to load these 4 bytes into A, and we'll just put the value here as 5. We won't write all the zeros and shit. And then we do the same for Y. We're going to load it into B. And that'll look something like this. And then we want to, you know, add the integer stored in B to the integer stored in A. And if we add that up, we'll get a, you know, a big old 8 in here. There you go. And the last thing we want to do is now store what is in A and jam that into the integer at address 1008, which is going to be Z. And that is more or less how this shit works. Let's take a look at a few more examples. All right, here's a situation where we've got an array, and we're going to do the same thing, but we're going to use array addressing. So how does that work? Well, I'm going to skip the steps where we initialize the array, but I just wanted to point out I've used some interesting values for the array. So here we have the value 16, and as you can see in hexadecimal, that is a 10 in the lowest order byte. 256 is going to be 00 and then 01 in hexadecimal. 65,536 is 0000 and then a 1 here, which is 1 followed by 4 zeros. And 65,535 is 1 less than this, and that's FFFF, like this. So this is the largest value, unsigned integer type value that can fit in, how many bits? 16 bits here. And this is 2 to the power of 16. This is 2 to the power of 8. And this is 2 to the power of 4. So yeah, just some different numbers, how you see them in decimal and how you see them in hexadecimal in memory. But anyways, that's not important. What is important is how we're getting this shit done. Well, let's translate this operation here. So we're gonna want to load values from the array, add them together, and store them. So what it's gonna do is it's gonna go integer at, and it's got to make a calculation here. So when the compiler puts space for the array in memory, it says, okay, the array is going to start at address 1000, and it's going to be, you know, 4 ints long. That's 16 bytes, right? Now, when you want to get at one of those, when you access, for example, array at index 2, what it's going to do is it's going to take the base address of this array, and it's going to add to it index, which is 2, times the size of an integer. And the size of an integer is 4 bytes, right? So this is going to be integer at 1000 plus 2 times 4 is 8. Integer at 1008. Store that into register A. And if you look down here, 1000, 1004, 1008, that is correct, right? That is element 2 in the array, 0, 1, 2. And again, it's going to do the same for element 3, which will look something like this. So when they're executed, they'll put these numbers in the registers. Then again, you're going to, you know, do integer add A to B. And that result is going to be, I'm not going to write it out or calculate, it's going to be about 130,000. It's easier to write out in hexadecimal. You'll see that in a second. And then you're going to store that back into array at 0. And that'll look something like this. And again, like adding these in decimal would be hard, but in hexadecimal it's easy, because you can see here that you've just got a 1 followed by 4 zeros, and then here you've got 4 Fs. So you just add F to 0, and that's just F. So the result is just going to be, it's going to be 01 FF FF, like this, which is, again, like I said, about 130,000, give or take, when written out in decimal. And that's it. Now, you might be looking at this and saying, wow, accessing arrays is actually, you know, it seems more expensive because you've got to calculate this index into the array. You've got to do addition, multiplication here. But the thing is, these values, so as long as this stuff is known at compile time, and the size of an integer is known at compile time, and this index, as you can see here, is known at compile time. So it will calculate all this stuff out ahead of time, and the CPU won't have to worry about it when it's running the actual program. All right, let's take a look at a situation of a class now. It's the same basic idea. If you got a class like this, it's got 3 members. Bush, an array of cars, which is called stones, and another int called pillar. And some of these have default values that they get initialized to when you create an object of that type. So we create an object J, and that's in memory here. Its address is at 1000, and then the addresses of its members are here, here, and here. Now, one thing that you might be noticing here that's a little strange is, well, if you look at the object here, it's taking up 12 bytes in memory. But if you look at the data, it's 4 plus 4 plus 2 is only 10. So why is it taking up the extra space? Well, you'll see here that there are some gaps between the member, the array stones and the int pillar. Why is that? And this is actually something that's worth talking about for a second here. Basically, the CPU, when it's loading from memory, it has a preference of where it wants to load stuff from. So if it's loading an integer is 4 bytes, and it's going to want to load those from addresses that are a multiple of 4. So loading from 1000, that's great. Loading from 1008, that's good. From 1004, it can load an int from there. But if you told it to try to load an int from 1001, from here, it can do it. It can do that, but it's not going to be happy with you, and it's not going to be an optimal arrangement. So the way the compiler does it is it will make it so that your ints are aligned to multiples of 4, and it does that by putting in padding between your members here. So you're going to get this padding here, and that is normal. You can turn that off, you can customize that, but it will slow your execution of your program down. So in general, you leave it at the default. You let it add padding between your members. It makes your objects a little bit larger, but it's better for speed. The CPU does not like to access unaligned memory. So integers, they have to have, the starting address here has to be a multiple of 4. Shorts would have to be a multiple of 2, so it would have to start at an even address. And cars are, you know, they're size 1. You can put them anywhere you like. Now let's take a look at this simple operation here. We're going to take an element in the member array stones, and we're going to assign it to the member variable pillar, which is an int. So first thing we're going to do is we're going to go, okay, well, we want to load the car at, and stones, well, first of all, J is 1000, right? So we've got 1000. Now, we've got to address into the object J. We want to get at the stones member. So we know that stones is, 4 bytes into the object J. So we just 1000 plus 4 plus, and this is an array, so now we have an index of 1 plus 1 times the size of a car, which is 1. So this is how you would access this element of the array, and you'll store that into A, and that will move the single byte from here into A. So now A is storing this single byte. Now we want to take that single byte in A and store it into pillar, but pillar is a 4 byte value. So we're going to need an operation here, and I'll just call it the operation car to int, and we do that on register A, and this will extend this. It'll add a bunch of zeros in front, basically. So now it's a 32-bit value, and then you're going to store A into, into the int at 1000 plus, and we're moving 8, pillar is 8 bytes into the object, so plus 8. And then there you go. There's this operation taken care of. All right, the last situation we're going to look at here is an array of objects of type junk here. So now we've got 2 objects in memory, and it's just going to be laid out like this. So again, we're going to omit the initialization code, and let's see what this operation here looks like. Well, first we're going to load stones 1 of the element 1 in the array of junk objects. So how we do that? Well, I mean, it's going to be obviously, it's going to be a car, right? Because stones is car. So a car at, and here's where it gets interesting. So the beginning of the array is 1000. So we put 1000. Now we have to index into the array. So that's plus index, which is 1, times the size of a junk object, which is 12. So now we are at the object, but now we want to get at stones at 1. So stones is going to be plus 4 into the object, and now we want to index into element 1 in stones, so that's plus index 1 times size of a car, which is 1. So this is the expression, expression for the indexing to get this piece of data here from this array of cars. And again, it looks like a lot, but this is all calculable at compile time. So the compiler will just, crunch all these numbers, and it will replace it just with the address 17. So it's just going to be load car at 1017 into register A. And the rest is just the same story as we saw before. And that's going to do it for today's lesson. Now, some of you are probably thinking, Chili, cool story, bro, but, where's the code? Where's the payoff? And, well, I mean, today's lesson was mostly just background that is going to help us to learn the lessons that come after it, the lessons about pointers and stuff. But, I mean, binary is useful. It's useful to understand binary for certain operations. And it's obviously important to understand the different kinds of basic data types you have available, the integer types, the floating point types. So that stuff is, directly useful. And the thing about the memory layout diagrams that I showed you, that I'm going to be using that information to help to teach you pointers. So yeah, trust me, Chili did not waste your time. As usual, I will drag you kicking and screaming, and in the end, you will thank me. Now, the other thing is that story that I gave you about the memory layout, how the different data types are arranged in memory, that isn't the full picture. That's just a simplification that will help us to learn about pointers later. If you want the full story, because I recorded a video that gives you the full story, and if you want that, there's going to be a link to that at the end of this video, also in the description, also on the wiki, so you can click that and you can get the full story, but it's optional, and I will not be referencing that in the main series here. So you can go ahead and watch that if you're interested, but don't get all fucking stressed out if it don't make sense to you, because like I said, it's a complicated thing, and it's optional. Now, since this video is mainly a theory video, there wasn't a lot of coding, I'm also not going to give any coding homework for this video. But what I will do is I will put up some questions. I'll put a quiz up on the wiki page, and you can try to come up with answers to the questions, and also put the answers in spoiler tags so you can check your answers after you're done the quiz. I hope you liked today's video. If you did, please click the like button. It helps a lot. And I will see you soon with some more C++.